design and development of a low-cost wireless network using IoT technologies for Mudslides monitoring systems. And the presenters are from Peru, from Meléndez.
Hello.
Hi, welcome to Eurocon 2021. Please proceed. No, I don't know if no sé si quieres hablar en español o en inglés.
My presentation, I'm going to English.
Okay, excellent. So we will continue with English, and Frank is working also with Ricardo Palomares and with Marco Milla, all of them from Lima, Peru. So please proceed.
Okay, thank you. Good morning. My name is Frank Enrique Meléndez Coveñas. A graduate of the Electronic Engineer and Telecommunication career at the National Technological University of Limasol. I'm going to present the topic of my paper titled Design and Development of a Low-Cost Wireless Network Using IoT Technology for a Mudslides Monitoring System. Okay, in the city of Lima, Peru, mudslides usually occur in the Jicamarca ravine, affecting the surrounding population and the Latarjea water treatment plant, as happened in 2017, when the plant reduced the production of drinking water to 15% for 3 days. The cleaning and maintenance cost of the plant amounted to more than $50,000 and more than 116 families were affected. The Jicamarca Radio Observatory, a research center of the Geophysical Institute of Peru, which is located near the Jicamarca ravine, implemented in 1998 a wide monitoring system which alerts the water treatment plant to close the floodgates avoiding contamination of drinking water and sends notification to authorities to take appropriate actions. The system is in continuous improvement, so the objective of the project is to implement a low-cost wireless network based on Internet of Things technologies for the wide monitoring system. Okay, network design. In Figure 2, the network scheme. The local network connects to the cellular mobile network through an access point that allows it to connect and transmit data to the cloud through the Cat-M1 backhaul and the MQTT protocol. The local network consists of the White-color station and the Rio Seco station. Both stations connect to the access point through the LR Wi-Fi network access protocol. In a monitoring station, the COAP protocol is implemented as a client, and in the access point, is implemented as a server. For the monitoring station, the expressive SPT2 microcontroller with an external antenna is used to take advantage of the expressive Wi-Fi LR mode. That allow it to achieve radio links of 1 kilometer of distance. Okay, Figure 4 action point scheme. The access point is also based on the SPT2 microcontroller in order to communicate with the same Wi-Fi LR mode. It also uses COMM SIM7000 modem that is in charge of establishing the communication with the cellular mobile network. In this project, the IoT Cat-M1 technology enabled in the SIM7000 modem was used to send the data to the MQTT broker on a cloud server. This made it possible to access the information to the internet from a PC of Jicamarca, of the radio observatory, of the Jicamarca Radio Observatory. The coverage in the world area was scanned using the Network Cell Info Lite program available for the Android operating system. The cellular mobile network of the telecommunication company Claro presented LTE coverage in band 28 compatible with the Cat and Band technology. Okay, the radio links between the monitoring stations and the access point were simulated in the radio mobile software. In both cases, a relative positive reception was obtained, which means that the radio links are viable. Okay, monitoring station algorithm. Monitoring station flow chart. The Wi-Fi and co-op client parameters are configured. Load rate is enabled to start the Wi-Fi link and the co-op protocol. If the monitoring station establishes the Wi-Fi link, the input data is taken and a co-op data transfer method is generated, which contains the input data to be sent to the access point. On the other hand, if the Wi-Fi link is not established, a maximum of 5 connection attempts are made. Okay, access point algorithm. The Wi-Fi co-op server and MQTT client parameters are configured. The data from the monitoring station are received. The SIM 7000 modem is turned on. The status of the cellular mobile network is verified. The connection is established through Cat and One by means of the IT commands. The data received by the co-op server is stored in a buffer. The SPT2 microcontroller transfers data to the SIM 7000 modem to its serial port. The SIM 7000 modem sends the data to the cloud periodically. The data is published on the MQTT broker topic. Okay, tests and results. The test one, data transmission from the monitoring station to the access point. Okay, in February 11, shows the monitoring station issued test data. So the co-op transfer protocol to the access point. It is observed that of the monitoring station is online and has successfully transmitted a data that at that moment was minus 76 dBm to the access point. In February 12, monitoring station Guaycoloro and Rio Seco shows monitoring station in field or also observed transmitting their test data, which in this case corresponds to their RSSI values. Okay, test 2, sending data to the internet to the cellular mobile network. By sending a series of 80 commands previously configured, communication was carried out between the SIM 7000 module and the cellular mobile network through Cat and One technology. Then the connection to the MQTT broker was established and the data transferred. February 13 show part of the flow of test data issued from the access point to the subscriber topic JRO SAT data. The monitoring station IP address and its RSSI value are published. Test 3, processing and analysis of results. According to February 14, the data is sent to the internet every 9.54 seconds on average. The system used by the Jicamarca Radio Observatory sends data approximately every 10 seconds. So the results are as expected. However, it can be affected by losses or degradation in the connectivity of connected smart objects. So it time takes a value greater than 12 seconds, a total of 11 times, being the longest latency time of 45 seconds presented on only one occasion. Okay, finally, cost. The wireless network based on IoT for multi-slide monitoring system has a cost of $231. On the other hand, the Liberium Smart Environment IoT Vertical Kit is available in the international market, whose sale price is $4,850. Table 1 presents the cost of the components of the wireless network designed considering 3 modules. These prices are reference prices. Okay, conclusion and future work. The low-cost wireless network based on IoT technologies is used as a multi-slide monitoring system. It was designed to operate under the environment condition of Lurigancho Chosica. This allows to send data every 9.54 seconds to the server in the cloud, with the aim of preventing exposure risk, and also can alert to the La Tarjea water treatment plant. Radio links of more than 1 kilometer using the SP32 microcontroller long-range mode allow the Guaycoloro and Rio Seco monitoring station to be located in hard-to-reach areas and far from the access point. The Catem 1 backhaul allows the transfer of data from the access point to a server hosted on the Internet. The IoT Co-op and MQTT network management protocols enable data control on devices with inexpensive, unconstrained hardware. The monitoring station, multi-slide monitoring center, will deploy monitoring system similar to the one reported here. This will be an effort in collaboration with different Peruvian institutions in order to contribute to the mechanisms for disaster risk reduction management in Peru. Okay, thank you very much.